Hello and welcome to this video. We are still working on measures of central tendency, and in this video I will explain what it means for a statistic to be resistant. Let's look at the following example. The following data represents the travel times in minutes to work for all 7 employees of a startup web development company, and we have our numbers. Suppose a new employee is hired who has 130-minute commute. How does this impact the value of the mean and median? So remember that we calculated the mean for this data before the new hire, and it was 24.9 minutes, and the median was 23 minutes. Now let's calculate the mean again after the new hire. It is going to be 38 minutes, and the median is going to be 24.5 minutes. As you notice here that the mean was substantially affected by the extreme value that we added to our data, which is 130 minutes. That's a huge number compared to the numbers that we had before. And the median did not get affected that much from 23 to 24.5, so almost 1.5 minutes difference, which is not a big deal. We say that a numerical summary of data is resistant if extreme values, very large or small values relative to the data, do not affect its value substantially. When data are skewed, there are extreme values in the tail which tend to pull the mean in the direction of the tail. For example, in skewed right distribution, there are large observations in the right tail. These observations increase the value of the mean, but have little effect on the median. Similarly, if a distribution is skewed left, the mean tends to be smaller than the median. In symmetric distributions or normal distributions, the mean and the median are close in value. And let's look at the graph here. So this is the graph to show you what I was just explaining. If the data was skewed left, then the mean is substantially smaller than the median. If the data was symmetric or normally distributed, then the mean roughly is equal to the median. If the data was skewed right, then the mean is substantially larger than the median. And that is because of extreme values that we have in the tail. In the case of the skewed left, we will have smaller values here. As they get closer to the zero, that means we have smaller values here, very, very small values compared to the main values that we have in our data. In the skewed right, we will have extremely big values compared to the numbers that we had before, and that's why they pull the mean with them. And they pull the mean with them because the mean is calculating the numbers, so they add the numbers and divide by how many observations we have, but the median does not get affected because we're just looking for the middle number of our data when we arrange it in an ascending order. Here's an example to see how can we apply the knowledge that we just learned to predict something about our data or the distribution. The following data represents the asking price of homes for sales in Lincoln, and we have all of the numbers in front of us. We want to find the mean and median and then use the mean and median to identify the shape of the distribution, and we want to verify the results by drawing a histogram for the data. So if we use Excel to calculate the mean is going to be $168,320, and the median asking price is $148,700. Therefore, we could say that the distribution is skewed right since the mean is bigger than the median. And to confirm this observation, we go ahead and create a histogram using Excel for our data. And sure enough, it confirms our answer and it is skewed right. So hopefully this helped, and I will see you in a different video.